My name is Tanner Davis, and I'll be presenting fracture mechanics with reactor pressure vessels. Reactor pressure vessels are designed to avoid failure during possible plant transients with defects in the material. A visual representation of the vessel with a crack is shown in the top right figure. An example of a transient considered is a pressurized thermal shock. This transient leads to a large decrease in temperature and pressure, as shown in the bottom right figure. Temperature affects the material toughness, and pressure affects the stress intensity near the crack. If these transient effects and defects are not accounted for in your design, the structure could possibly fail during the transient. In your design analysis, the types of fracture mechanic parameters considered would be your crack geometry, initial crack location, and initial crack depth. Your evaluation would select the limiting combination of these parameters to maximize the stress intensity factor, and you would adjust your design to compensate for this factor. These parameters would most likely result in you maximizing the tensile force or hoop stress acting on near the crack. However, it is unlikely that you would design for every possible defect. This would ultimately result in you setting a design requirement to be met by the manufacturer. In addition to the fracture mechanic parameters previously mentioned, you'll need to consider the parameters listed below, as well as the uncertainty in these parameters. Overall, each of these parameters is affecting your goal, shown in the figure to the right. The figure is a plot of toughness versus your plant temperature. Your goal is to remain below the material toughness during the transient with some amount of margin for your design. However, your design could run into problems in the future if the manufacturer cannot meet these requirements, or even worse, the plant is operational and one of these parameters was determined to have a larger impact than expected. This raises the question of whether is this an actual concern. There is a method to alleviate this problem, which we'll cover in the next slide. As previously mentioned, your initial approach was a deterministic analysis in which you evaluated the worst possible scenario of all parameters. However, it's unlikely that all these conditions can occur at one time. A probabilistic approach will determine a more realistic response. An example is shown to the right, in which your limiting crack depth could be highly probable, but your limiting crack orientation can be very unlikely to occur. This could be based on manufacturing data which determined the cladding material is welded in a certain way that avoided this particular crack orientation, as an example. And this would give you a distribution which you could apply into the method that we'll discuss in the next slide. So with your distribution of parameters, you can now use the method shown to the left to determine the probability of failure. Methods such as Monte Carlo will be used to randomly sample each parameter, and the value of that parameter would then be combined with the FEA model and/or transient model to determine whether the vessel fails or not. Your end result would be the probability of failure based on the equation below. Again, this would quantify that not all limiting fracture mechanic properties are likely to occur, avoiding concerns of structure failure. However, there is a downfall of this method, is that it's very analytically intensive, as you must run your detailed FEA model numerous times to get a realistic answer. Thank you. I hope you enjoyed the presentation.